Today I'm very happy to share our research about spatial temporal representation learning for urban data analytics. My name is Kaiqi Zhao, currently a senior lecturer with the School of Computer Science. I would like to thank Sebastian to introduce the work of academic staff and what is expected in their work. So basically, I focus on research in geospatial data. So nowadays, I believe that all of you should have been using a lot of smart devices like smartwatch, tablets. In many of the vehicles that you are driving, they're also equipped with the GPS functionalities. So nowadays, we can accumulate a large volume of data from social media as well as from vehicles. It is very interesting to look into this massive amount of data and to conduct analytics on the data and find some valuable information or patterns from it. And of course, also visualization, as Simon just mentioned. So basically, in geospatial data mining, we often focus on several types of data. The first type is point data, which include the point of interest data, which are locations that the user may be interested in. For example, restaurants, stores, university, etc. Besides, we can deploy a lot of different sensors in the urban cities, including traffic sensors, as well as environmental sensors. So based on this point of interest data and sensor data, we can conduct PR recommendations or time series predictions, etc. So we have published several papers on the top values in the data mining area. The second data type is sequence. So basically, we can keep track of the GPS points, which forms GPS traces. We can also have the users check in data on different points of interest. So based on this sequence data, we can perform similarity computation, trying to measure how similar two trajectories are, and conduct anomaly detection, which tries to identify anomalous trajectories even on the fly when you are driving. And we could also conduct research about next PR recommendations, trying to recommend the next move of a user based on the current traces. Besides, we also have a type of data called regions. Regions is relatively less studied in the area, but it's still very important. For example, if you try to analyze the urban function of different regions in an urban city, or you are trying to conduct some urban planning task, you need to understand the spatial configuration of different regions. So based on the geographical regions, we have actually done some research about similar region search, geotopic mining. We mentioned a lot of different spatial temporal data mining tasks, but one of the problem is that how do we represent such kind of data? This is the essential problem sitting among all these data mining tasks. Of course, one may say you can use the raw representation of entities, for example, the coordinates, the latitude and longitude value of coordinates to represent the location. You could also use the word tokens to represent the text. But using the raw representation itself, we have several limitations. First of all, the attributes of the geo entities will be considered separately. And you will lose the interdependency among different attributes. And besides, you may also lose the information from the spatial temporal context, because each geo entity in the geographical space is not standalone. You have a lot of different POIs, point of interest, located nearby. And if you look into the time dimension, those information, or for example, user reviews posted on the POIs will change over time. So the topics around those point of interest will also change over time. So by looking into just the raw representation of the geo entities, we are not able to capture the spatial temporal context. So what people do in the past is that they try to design very complicated models to capture those interdependencies. For example, previously people designed graphical models trying to capture the interdependencies and make predictions. And nowadays, thanks for the representation learning techniques, we are able to learn a rich and compact representation of geo entities using a data-driven approach. So you don't have to worry about the design of a very complicated model for the prediction. If you have a way to learn the representation for the geo entities, and you can pre-train the embeddings, then when you try to employ this representation for n task, then you can just use a very simple predictors rather than a complex model like graphical models. Okay, so the benefits for representation learning is that it is very easy for computation, since computers often manipulate on numbers, vectors, tensors, right? So if you can convert those attributes of geo entities as well as their spatial temporal context into the representation space, we are able to capture those information and then use a simple predictor to perform the predictions, but with a good performance. So the essential problem here is that how to encode the intrinsic features as well as the extrinsic spatial temporal context in the learned representation of the geo entities. So now I would like to give you a brief introduction of two of our work around representation learning for geospatial entities, including for point data and sequential data. So the first one is about time series imputation or estimation. So basically, the pitfall is that we do have a lot of sensor data around the city, but the thing is, many of those sensors face the issues of missing data. We often have missing data due to different reasons. For example, for energy consumption purpose, sometimes we might adapt the sampling rates of those sensors. On the other hand, sometimes we also have some defaults, some device faults, so that we might have some missing values. So to address this problem, actually there has been a lot of research that use statistical approaches. For example, using mean, KNN, mice, etc. Some other approach try to capture the temporal dependency of the time series data using deep temporal models. And more recent research used the spatial temporal models that try to capture the correlation between different sensor locations when they try to estimate the values. But they have assumption that the graph structure, the dependency among different sensor locations are static. However, we observe that dynamic spatial correlations exist in the real-world data sets. For example, we analyzed the weather data from Netherlands, and we observed that the different geographical stations have high correlations during different time periods. Also, these dynamic spatial correlations may exhibit periodic patterns. So you can see that this green circles denotes that the correlations between two stations increase and decrease and increase again. So the question here is, how do we capture this kind of mixture of dynamic patterns in the correlations between the sensors. And besides that, we are also interested in looking into the inter-feature correlations. That means the correlation between different features, for example, the wind speed and wind direction, because we believe that those features may have some inherent correlations. Okay, so to address these limitations, we propose a multi-view learning framework. So this figure looks quite complicated, but I would like to just mention that we model the correlations from different views. You can see there are 3 views here, and each view captures the correlations from a specific perspective. For example, the first view captures the correlation between features, and the second view captures the correlations regarding to a specific feature, for example, time, for example, wind speed or wind direction. And the last view tries to simulate the diffusion process of an event, a time series event, and how it propagates along the time and across locations. And based on these 3 views, we can form a comprehensive view of the time series data and obtain its representations. And after that, you can use a simple predictor to make predictions. We conduct our experiments on several data sets with different number of features, different number of nodes, and time steps. And here are some results of the proposed method DAMR, which achieved the lowest error according to compared to the state-of-the-art approaches. And we also want to mention that the proposed method achieved relatively comparable running time cost compared to the state-of-the-art model. The reason is that even though we consider different views for the multi-view learning framework, we do not need to design a very complicated model for a single view. So each view will be handled by a quite simple model, instead of designing a very complicated model that just captures the correlation from the single view. So in this sense, the complexity is not high for the proposed method, but at the same time, we achieve a better performance compared to the other approaches. The other research problem that I would like to briefly mention is the next POI recommendation problem. So for point of interest data, which consists of the check-ins of a user visiting a POI at a specific time. For example, you can keep track of the user's movements from, for example, train station to office to gym and to restaurants. And the task is that we are trying to guess what is the next move of the user, given the historical check-in sequences of the user as well as the recent check-ins, for example, those in a couple of hours. This task is a common task in location-based services. There are some research on this research problem, but most of them consider this as a sequential modeling problem. But they have some limitations. They are less effective for short trajectories, because if you model this as a sequential model, then that means you need a sufficient number of check-ins in order to capture the sequential information. But if the trajectory is too short, it's very hard to capture the patterns. The other problem is that if you model that as a sequential model, then for those inactive users with very small number of check-ins, it's very hard for us to capture the patterns as well. And another limitation is that they often omit the temporal patterns of POI categories. So as you can see on these figures, different types of POIs, train station and bar may exhibit different temporal patterns. And these temporal patterns is very useful when you try to guess the next move of the user given some specific time point. We also noticed that there is no silver bullet exist in finding a perfect solution, right? To address the scarcity issues that I mentioned before. But we can actually leverage the collective information from all other users, the wisdom from the people, right? So if you observe that most of users transit from restaurants to theater, then you might probably be able to recommend theater after viewing the check-ins at restaurants. Even though you just observe the user visit gym and then restaurants, you can have I guess a high probability that a user will visit the theater. So based on this idea, we propose a graph enhanced transformer GetNext, which has attracted much attention in recent years. And just in 2 years, we reached to 100 citations for this paper. And it is the first one that's trying to incorporate a transformer into the context of next point of interest recommendations. So the idea is to use the collective trajectory flow map, which is a graph that is constructed from the check-in records from all the users. And we also integrate the user's preference, spatial temporal context, and time-aware category embeddings into the framework. So basically, the proposed method can be simply divided into 3 parts. The first part is to learn the generic movement patterns from all the users. So the center is to construct the center idea is to construct a trajectory flow map, and then employ graph neural networks to extract the local transition patterns of the POIs. And the second part is a contextual embedding component that tries to capture the correlation between time and category, and as well as the correlation between the users and the POIs in order to encode the spatial temporal information of each check-in records. And based on this, we run a transformer encoder to capture the independencies among different check-in records and make predictions based on a simple prediction model. Essentially, this is a MLP, multi-layer perceptron. So instead of just predicting the point of interest, we also predict the time and category in order to enforce the encoder to encode the information of time and category. So only when the encoder can capture the time and category, the decoder can generate the time and category. We evaluate the model on 3 datasets, 2 cities from Foursquare and 1 from Guyana. And we can see that the performance of the proposed method is better than the previous methods, but that is not what I want to focus. What I want to focus is that if we look into the short trajectories, we can see a large improvement compared to the state-of-the-art method. That is because we consider the generic movement patterns. So even we have very little information of the current trajectory, we are able to give a good prediction for the next move. Yeah, so as for the inactive users, we can also achieve a great improvement compared to the state-of-the-art model. Okay, so this is a simple summary of the talk. So I have mentioned 2 tasks in spatial temporal representation learning, including the time series imputation. And actually that method can also be applied for prediction forecasting. The second task is about next POI recommendation. And there are several interesting future directions as well, including multitask learning, trying to build a model that is able to handle very different tasks. And also zero-shot learning that tries to learn a model from a city that is applicable to another city without fine-tuning. The second direction is urban foundation models, which is an idea very similar to large language model, but this is in the area of urban computing. So because the urban data is quite different from natural language data, where we have structure, we have graphs. So we believe that the current large language model is not sufficient to handle heterogeneous tasks in a very good manner. So even though we have large language model for POI recommendations nowadays, but they still have a lot of limitations, including that they must know the point of interest before they can make recommendations. Another perspective is that we could build an urban knowledge graph that include all the point of interest, the road networks information, and we can maintain and update the knowledge graphs so that even though you have an outdated foundation model, we can use the new knowledge to inform the model and improve the performance of the foundation model. So this is all about the talk, and we have also written a new survey paper, and if you are interested in, you can just refer to the link. And the survey paper is about geospatial AI with a specific focus on self-supervised learning. Okay, thank you very much.
Question? Go for it.
So I have a question about scalability. So, it's really fascinating. I find it really interesting comparing these things because I'm really interested in spatial temporal movement, especially human movement. So how does it scale if you're looking at millions of users, millions of transactions? So
I think the model is linear to the number of users, and it's not an issue for scale to large data.
And is it also with respect to building the network? So that's fine.
The construction of the network. The construction of the network should be the most time-consuming part, but that could be constructed offline with one pass, one scan of the.
So I don't mean necessarily inference. I mean actually the construction part. So if you have millions of users that you're trying to build the network from, if that's how scalable is that?
Yeah, but that could be done in one pass. So you have a database. We have a database of the check-in records, as you can see here. So we can scan this one line by line and create so it's proportional to the number of records that you have.
Okay.
Yes. Any question?
Do you know of any plans from governments to make use of that?
You mean
any government? I don't know.
Any government. At least I understand in China, there are some research projects in this area, and they also build the urban knowledge graph. They have started to create that one, and they also have some projects on building, a geospatial model for the smart city, because their city, I think, is quite smart because they have many sensors there, and they can collect a large amount of data. And from that perspective, yes, they, especially in Hangzhou, I'm not sure if you know, they deploy a lot of sensors, and they have a thing called City Brain, and which is the data science center of the whole city. So like a digital twin, but it's not exactly the same thing, because digital twin is kind of simulating the city, a digital copy of the city, but they do a step further to analyze those information, including the traffics, all the traffics, and also the environment's data. Yeah.
I think, for example, also Google Maps and something like this. They could provide a lot of data, but they would also obviously, I would think they would also have an agenda in that regard.
Yeah, Google Maps also have the data, and they have a lot of street view images that is able to help build the foundation model. I believe that in the internal of Google, they are also trying to work out a method, a model for that. But from the perspective of universities, we could also leverage some open source data. For example, OpenStreetMap, which includes the point of interest and road networks from all over the world. So that data should be large sufficient. But apart from that, satellite data and street view data is also complementary to that.
One question.
Yeah.
The concept of urban foundation models is quite interesting. So is there any work on somewhere like in research institutions out there, something that is already out there?
So far as I know, foundation model, well-established foundation model for urban city is not yet there. But there are some foundation model, as you know, you could think of GPT as a foundation model for language, right? But it has very large limitations to be applied to the urban city perspective, because urban city is not actually, urban data is not actually a sequence, right? So if you flatten that information to a sequence, you will lose a lot of information. For example, the spatial neighborhood of the data, right? We can do that. We can actually flatten the data, and some research has done from this perspective. But yes, as I have mentioned, there are limitations for large language model for handling this data. Yeah.
Yeah, and probably the other challenge is not all cities collect the same way data from the sensors in the same way, right? So
yeah.
I don't know if you build a foundation model for Auckland, will it be applicable in any other city, New York?
Yeah, that's as I mentioned for the zero-shot learning, and actually, if you can imagine that many of the traffic patterns are similar, right? When you drive, the behaviors might follow some rules, and if the model is able to capture those rules, then this can be applicable at least to the areas with similar traffic rules, rather than you cannot apply the New Zealand one to China because they are actually quite different. Yeah.
I can give you an example. I'm from Melbourne, so I come to the street. There's this data competition, and we had 1 year competition for, now we have trams. So everyone swipes on, swipe off like you do with buses. So we had data of cards that swiped on and swiped off. So an example was we had what we call it, the Australian rugby league. I don't follow it, so I'll call it rugby league. So the stadium traffic that goes to it. So you could actually analyse data of a high population of people catching the trams at a certain time that were part of that fan of that team that was playing at that stadium. So at the end of the day, the tram company can put on the trams in the future. Yeah. That's just an example. Yeah. So I take it you can AI for that.
Yeah. Thank you.
Okay, thanks.
Okay.